Good morning.
Good afternoon. Close enough.
I slept in.
Yeah, it's 1 o'clock. So, hey, everyone, just to let you know, my power went out a little while ago. I know some of you also had that same thing happen. So, you know, if I lose power, then I don't know what'll happen. But CPS told me it's back, so I'm going to go with that. So, all right. So I'm going to start with a quiz today, like we did last time, because I think you all enjoyed that quite a bit. So we're gonna see how this goes. All right, so I'm gonna launch a poll. It's gonna be just like kind of like the last time. There we go, it's launched. And then here are the questions. So it's multiple choice. I give you, there's 2 problems here. Use implicit differentiation to take the derivative with respect to x. Do not try and solve for dy dx. All I want is you to just show me how to take the derivative. And then one of those options, A, B, C, or D, is going to be the correct differentiation of this with respect to x. So enjoy. We'll take a few minutes here, see how it goes.
Professor Giovanni. Hello? 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 Hello?
I guess he's not here.
I can't see the bottom part for number 2.
What do you mean?
Okay, I can see it now.
Did anybody have a problem with the poll opening up? Because it didn't open up for me.
I've got it.
There should be a button at the bottom bar that says polls that you can click on to pop up.
Yeah, it's not letting me. I'll have to talk to him when he comes back.
Yeah, I'm here. Just if your poll's not coming up, then send me a chat with your answers.
Man, my screen is tripping. I can't see D. There it is.
Is that a question? I'm sorry, what?
Oh no, it was my screen was tripping. I couldn't see it.
Okay. And so right now, a little bit more than half the class is done. I'm going to go 3 more minutes.
Sir, can I resubmit one of my answers?
I don't know if it'll let you. And so if you want to change something, just send me a chat.
Sure.
1 minute. In 10 seconds, I'm going to close it out. Okay, you should see the results. So on number 1, we have 100% of you that responded said C, that's correct. And then on number 2, a little bit more of a variety here on the answers. The correct answer is B. So I'll run through this quickly. Close this out. Okay, so on the first one, we're differentiating with respect to X. So that means that the derivative of 4, of course, would be 0. All right, so it can't be this one. Can't be that one. Well, hold on. Sorry, I shouldn't say that. Let's just go through it. Derivative of 4, 0. Derivative of x is with respect to x is 1. X squared is 2x. And that's because we're differentiating with respect to x. So everything's going to be the way it used to be. And then this is 3x squared. Now on the other side, it's a little different. We differentiate y with respect to x. That's dy dx. And then we differentiate y squared. We first do the chain rule, so we get the 2y first. Then we take the derivative of y, which is dy dx. Then we say plus, now we take derivative of something cubed. That's going to be 3 times that something squared. And then chain rule again, take the derivative of y, you get dy dx. So C. Now on number 2, on the left side, we have to take derivative of sine of something, right? Which should start off by being cosine of the same thing. So that automatically eliminates the first one because we have to have cosine of x plus y for sure. And then you're supposed to multiply that times the derivative of what's inside. And these are 2 terms separated by addition, so you do them separately. So derivative of x is 1, and derivative of y is dy dx. So that means can't be this one. It's got to be one of these 2. And then we say plus, now we have to take derivative here, and this is a product rule. So you have to apply the product rule to this. So first you take derivative of x squared, which is 2x, and then times y cubed, that's this. And then plus the derivative of y cubed, which is, again, chain rule, 3y squared times dy dx, then times the first function x squared, then equals the derivative of x, which is 1. So that's it. It's hard to make multiple choice for this because it's hard to figure out what you would do wrong, right? Like there's little places where you might, like on this one here, the difference between these 2 is on this one, you did the product rule correctly, but on this one, you don't do the product rule, you do each one together, like just one at a time, which is wrong. So, okay.
That's the one. That's the one that got me, sir. I chose C for that one. I looked at it again. I was like, oh.
Yeah. Okay. So you didn't do product rule. You just did each one.
Yeah. I was doing it in my head. And then I was looking at the answers again and I realized that, yeah, that was product rule. I didn't go through the process. So.
Okay. All right. So we have more to do today. Let's see here. We're going to continue in this section. We're going to finish it off and then we're going to start the next section. I sent everybody an email earlier today that had something called the related rates worksheet. If you didn't get that, I'll send it through the chat in just a little while. All right, so I thought we would start class with this one. Find the equation of the line. So we've been doing derivatives, right? We've been doing implicit differentiation to be able to find dy dx. Now let's see how we can use that to actually go back and do something we had before, which is find the equation of a tangent line. So we're trying to find the equation of a tangent line to this really strange looking equation. This is an implicit equation because you cannot easily solve for y. The graph of this equation, oh, and we're supposed to look at this 0.31. So the graph of this equation looks like this. Kind of cool. And what we want to know is what is the equation of the tangent line at the point 3,1. So if you go out 3, go up 1, right there, what's the equation of that tangent line? I think we can kind of imagine that the tangent line is going to look something like this. We want the equation of that, right? So let's see. I have not done this problem. So I'm going to graph the tangent line when we get it, and we'll see if it works, okay, if it matches up. So let's start with the derivative. This is a mess, okay? So with this equation, I'm going to differentiate both sides of the equation with respect to x. The reason why I'm doing with respect to x is because the equation of the tangent line requires that we find y prime, right? The derivative, the slope of the tangent line, which for us, we know means dy dx. So I'm going to take the derivative with respect to x on the left side of the equation. And then that should be equal to the derivative with respect to x on the right side of the equation. All right, now when I do the left side, even though I have a sum here, right? These two are separated by addition. All of this is being squared, which means I have to do chain rule. So I'm going to look at this as being a bunch of stuff here squared, right? And it's actually 2 times a bunch of stuff squared. So when I take the derivative, this 2 should come for the ride, right? I should have that 2 should come down. But then when I do the derivative of something squared, I have to do power rule. So the 2 comes down, that's this 2 coming down. And then I have everything that's inside, I don't touch that yet. And then it'll be that to the first power. So that's just your power rule, doing that blue part first. And then by the chain rule, we're going to say times, and now you're allowed to take the derivative of the inside. And when I do that, this is where you can say, oh, I've got 2 terms separated by addition, so I can do them individually. So I'm going to take the derivative of each one. So what's the derivative of x squared?
2x.
2x. And then this is the one that's tricky, the derivative of y squared.
2y dy dx.
2y dy dx. Any questions on that? And by the way, this right here, this is a 1, right? Don't confuse that with, I'm not saying a prime, it's not a derivative. I'll put a little, I'll make it look more like a 1. Okay, we are done on the left-hand side. We did the 2 out, this to the first power, then we took derivative of the inside. I must have these parentheses here. These must be here because this is 2 terms, and we're multiplying this times whatever that turns out to be. So if you're missing the parentheses, it's going to throw everything off. Okay, equals. All right, now on the right-hand side, again, I have a 25 sitting in front there, so I can just bring that for the ride. And then I'm ready to take the derivative of what's in here. And it's 2 terms, right? I don't have that chain rule this time. I don't have a power to bring down. So I can just do them individually. And here I'll get 2x minus 2y dy dx. Questions? All right, now normally, like in your homework problems, you were asked at this point to go solve for dy dx, right? You go get dy dx by itself, which is really an algebraic pain in the butt, right? But because this problem is actually asking us to find dy dx at a specific point, right? They give us a point. I can actually avoid the solving for dy dx by just replacing x with 3 and y with 1 in this equation right now. And it'll make it much easier to solve for dy dx once I do that. So everywhere I see an x, I'm going to replace it with a 3. Everywhere I see a y, I'm going to replace it with a 1. So here's what we get. 2 times 2. X is going to be replaced with 3. 3 squared plus y is replaced with 1. 1 squared. Okay, separate parentheses. 2 times 3 plus 2 times 1 dy dx equals 25. 2 times 3 minus 2 times 1 dy dx. Understand? Let's clean this up. This is 4. And then in this parentheses, I get 9 plus 1, that's 10. Then in this parentheses, I get 6, 2 times 3, plus 2 times 1 times dy dx is plus 2 dy dx. I have to sneeze. Whoa, okay. Equals 25, and then in parentheses 6 minus 2 dy dx again. Now you just got to make sure you do everything properly here. I'm going to do 4 times 10, that's 40. 6 plus 2. Now look, do we all understand dy dx is y prime? Like, we understand that. I'm going to replace that dy dx just with y prime. It's just a little easier for me to write. that instead, equals, let's distribute the 25 through here. So what is 25 times 6?
150.
50, and then distribute here, we get negative 50 y prime. Again, I'm replacing dy dx with y prime. Distribute 40 through here, 240 plus 80 y prime equals 150 minus 50 y prime. I'll take all my y primes to one side and all my numbers to the other. So if I add 50 y prime to both sides, I get 130 y prime. And if I subtract 240 from both sides, I get negative 90. And last step, I will divide both sides by negative 130. And I'll just leave that as a fraction. I'll just reduce it. That becomes 9/13. That doesn't seem right.
Divided by negative 130, it should be positive 130.
Oh yeah, I'm sorry, I'm dividing by, I was like, we should have a negative number. We're dividing by positive 130. Thank you. That'll give us negative 9/13. All right, that's the slope of our tangent line, right? That is the slope of the tangent line at that point. We want the equation. So now we go back to this good old formula that's been our friend for a long time now in this class. We have the slope, right? Negative 9/13, and we have the point. The point was 3,1. So if I use this point 3,1, I replace the y1 with 1, the slope with negative 9/13, and then replace the x1 with 3. That should be the equation on the tangent line. Now I can go solve that for y, right? But I'm just going to leave it like that because that is an equation of a line. And now I'm just going to go back to the graphing software and cross my fingers. Ready? Y minus 1 equals negative 9/13 x minus 3. There it is. That looks pretty tangent to me. All right, tangent to that curve at that point. There we go. Okay, questions on any of this work? So if you are asked to find the equation of a tangent line to some implicit equation, you do your derivative with respect to x on both sides, then just replace the x and y. I recommend that you do not go try and solve for dy dx algebraically. That's just my advice because there's just a lot of room for error there. If you plug in numbers, I think everything kind of gets a little easier, all right? Now, if you're just asked to find dy dx, you have no way around it. You have to go solve for it. All right, let's look at another problem. Question, what?
It's a quick stupid question. So back when you said you were doing the chain rule, you said you didn't need to do the chain rule on that one because it didn't have a exponent? Just
right here on this one? On this right here, when I was taking derivative of that, this whole thing was not raised to a power other than 1, right? I mean, you could, if you wanted to, imagine that there's a 1 here, right? But like on this one, we had to bring the 2 out and do 2 times this to the first power. We don't have to do that here because it's 1. So all we do is just derivative inside. Now technically, could you do it? Yes. But watch what would happen. You bring the 1 out, so you'd have 1. Then all of that, don't touch it. To what power though?
Just multiply by 1. So yeah,
E to the power of 0.
It would be to the power of 0, right? Because you subtract 1 from that power when you bring it down. And then anything to the 0 is 1. So basically this whole thing turns into a 1. And then you say times, now you do derivative of what's inside, which is this. So it's like all of this crap right here is really like a 1 right here. You don't need it. I'm not suggesting you do that. It's saying like, even if you follow the rules, it would still give you the same answer. Okay. This one is interesting. So there are a few problems at the end of your homework that they ask you to find y double prime. All right, y double prime. So I just want to make sure everyone understands this before I start this. Y prime for us means dy dx, right? And it's that way because we just all agree that's what it means. But I told you already, class ago, that y prime by itself really doesn't give you all the information you truly need. It doesn't tell you what you're differentiating with respect to. That's why this notation dy dx is so much better. But as long as we all agree that y prime means that, then y double prime should mean the second derivative with respect to x. So this is just Leibniz notation of the second derivative. Go back into your notes when we were talking about notation. How do we notate a first derivative, second derivative, third derivative? This is just the notation for the second derivative. But for us, again, I just want us to all just make sure we're on the same page. For this class, for today and for moving on, if we write y prime, we mean dy dx. We write y double prime, we mean the second derivative, okay? So here I go. I'm going to start trying to see if I can get y double prime. And the first thing I'm going to do is just figure out what y prime is. So I'm going to just take the derivative with respect to x of this equation. Now, I didn't state this, I guess not clear enough, that when you see equations, if you see letters in here other than x and y, like if you see a or b or c or d or something like that in there, or a k or an n, you assume that those are constants. The variables that we use in this class are usually x, y, z, t, theta, okay? But if it's something other than that, like lowercase a, b, c, d, that is generally a constant. And there is some page in the book, and I have not been able to find it, but I know it's in there that states that, like in the beginning of the book. It says, if you see these lowercase letters, those are constants. So we're going to take the derivative with respect to x. Now I'm going to try and move a little faster here through this. I don't have to write down each step. So let's just kind of see if we can make sense out of this. This is plus between these two things, so I'm going to do them individually. I'm taking derivative with respect to x, so the derivative of x to the fourth should be 4x cubed. And then I'm going to add to that the derivative of y to the fourth. Now here's where I need the chain rule, right? You're going to get the 4y to the third power, but because of chain rule, you now need to multiply times the derivative of y, which is dy dx, right? dy dx. And I'm done on the left side, yes? Did each one? What about the right side?
Well, you said that was a constant, right? 0?
I'm telling you A is a constant. So
Then that should just be
it's
0.
a number like 2, right? 2 to the fourth power. That's still a constant, right?
Yeah, it's just 0 then.
So the derivative is 0. It does not matter that's to the fourth power, because if I take any number and raise it to the fourth power, I'm just going to have a number, right? It's a constant still. So there is my derivative, right? This is differentiating with respect to x. I'm going to rewrite this a slightly different way. Again, just to make my notation a little bit cleaner. See how I'm using the y prime instead of the dy dx? Now, I need the derivative again. I need the second derivative, right? The second derivative. So watch what I'm doing. Take the derivative again with respect to x on both sides. Derivative with respect to x of the left side. Now, when I take the derivative on the right side, that's a constant again, so derivative of constant is 0. On the left-hand side, I have two terms, right? This one and this one. So I'm doing it individually. When I take the derivative of 4x cubed by itself, right, I get 12x squared. You with me? Plus, now, this is the tricky one. This is a product right here. I'm going to look at it as a product between 4y cubed and y prime. There's a product right there. So I'm going to apply my product rule, right, to this. So let's carefully do that. If I asked you for the derivative of this product, you would take the derivative of the first one times the second, plus the derivative of the second one times the first one, right? So what is the derivative of the first one?
12y squared dy dx.
12y squared, then?
Dy dx.
Dy dx, right? Because you have to take derivative of the base again. Now, I'm not going to write dy dx. I'm going to write y prime. Is everyone clear that that is the derivative of this with respect to x? 3 comes out, you get the 12y squared, then you take derivative of y, that's dy dx, which I'm writing as y prime. Now I need to multiply that times what?
Y prime again.
Y prime again, right? Now, y prime times y prime is not y double prime. That's the first derivative times itself. That's the first derivative squared. That's not the second derivative. I'll show you when we get to the next step. Okay, plus now the product rule, right? Now I'm going to look at the second one. I have to take the derivative of that one and then multiply times this, right? But what's the derivative of the derivative?
Y double prime.
Right, that's the second derivative. It's the derivative of the derivative. So that's where I get my y double prime to come out. Then I say times now the first one, 4y cubed.
How would you write, like instead of y double prime, how would you write that in the dx to dy dx notation?
Okay, good question. So had I done this way, had we instead written this as dy dx, right? Had we written it that way, then when I do my derivative, I'm going to get my 12x squared, that's off of this one, plus, now here's my product rule, 12 y squared times dy dx, right? That's just derivative of this right here. Now I need times that, right? Times this. Plus, now you're asking me, how would you write the notation for the derivative of this, right? So maybe it'll help if I write it like this. We're trying to take derivative of that, right? So I'm trying to take the derivative with respect to x of the derivative of y with respect to x, right? One way you could look at that is, see you have two d's across the top? You can look at it as like d squared y over, and then on the bottom, do you see you have two dx's? So you could put like dx squared. And that's the exact notation of the second derivative. So that's what you would put here. You write d squared y over dx squared. That would be the derivative of this one. And then you do times the first one equals 0. Does that answer your question?
Yeah.
Okay. Let me clean this up just a little bit. We've got 12x squared plus, watch this part, 12y squared, y prime squared, plus 4y cubed times y double prime equals 0. So the only thing I did here was I put these y primes together. There's multiplication between them. So when I multiply the two, it's the same as squaring it. So I'm squaring the first derivative, right? Squaring the first derivative. Plus, and then I just move the 4y cubed out in front of the y double prime. Okay, now let's try and get y double prime by itself. So I'm going to leave the 4y cubed y double prime on one side, and everything else I'm moving to the other side. Negative 12 x squared plus, minus 12 y squared y prime squared. So just move those two terms to the right, left this one here. And the last thing would be to divide by 4y cubed, right? You just take this divided by y cubed. Uh, 4y cubed, sorry. Do you understand? So right now, if you wanted to know what the second derivative was, what information would I have to give you for you to be able to tell me what the second derivative is?
The first derivative?
I would need to know what the first derivative is, right?
Yeah,
and I
we
would
know.
need to know the x and the y.
Yeah.
So there's actually three things you would have to know. You'd have to know the point we're talking about, the x and the y, and you would have to know the derivative at that point also. That's a lot to have to know, isn't it? To have to be able to figure out the second derivative. So this technically is correct, but this is not the answer in the back of the book, okay? So let me show you, I don't have it up anymore. I'll show you the answer in the back of the book later, but let me show you how they get to it, okay? So what they do is they say, all right, I don't like this y prime here because I don't want to have to figure out what y prime is to get this answer. I just want to know what the x and the y are. Give me the point, and that way I can give you the second derivative. So we go back up here to this part of the problem right here. Right here, sorry, this right here. Do y'all see that where we had taken the derivative that first time? I want to take that equation and let's solve it for y prime. So if we solve this for y prime, we would get 4y cubed y prime equals negative 4x cubed. Agree? Just move this guy over to the other side. Now divide both sides by 4y cubed.
And then we could substitute that in for our y prime.
We will substitute that. Now I'm going to simplify it a little bit. It's negative x cubed over y cubed because the 4's cancel, but we still have a negative there, right? So that's what y prime is right there. And that y prime is now in terms of x and y. So I can take that answer and plug it in right here. So y double prime is equal to negative 12x squared minus 12y squared. Then I'm going to take that answer I just got, negative x cubed over y cubed, and square it. And then all of that over 4y cubed. I know that looks terrible, all right? But that's what it is, right? I mean, that's it. Let's square this, okay? Let's square this thing. The final answer is going to be so weird when you see it. Okay, if I square this fraction, the negative goes away because I'm squaring it. I square the top and bottom. That means I'm going to take 3 and multiply by 2 on both of these exponents. So it'll be x to the 6th over y to the 6th. No negative anymore, right? Over 4y cubed. I'm going to clean this up a little bit more. I have negative 12x squared minus, okay, let's see. This y squared is on top of this y to the 6th. So I can rewrite that as negative 12x to the 6th over y to the 4th. All I'm doing there is reducing that out, right? Just canceling 2 of the y's. All over 4y cubed. Y'all still good with that? I'm going to get a common denominator on the top. I'm going to put these two together, which means I need to rewrite this as this over 1 and then multiply by y to the 4th out front on top and bottom. That'll give me a common denominator so I can put them together. When I do that, on the top, I'm going to get a negative 12 x squared y to the 4th. And then I have on the other one, the minus 12x to the 6th over the common denominator, which is y to the fourth, but that's all on top of 4y cubed. Y'all still with me? It's just algebra, but I mean, it's hard to know where we're going, right? It's like, where are we headed here? Why am I doing all this? Like, when do we stop? Something really interesting is going to happen. Watch. In the numerator, you see this up here? In the numerator, just up here, I want you to factor out a GCF. So what can you pull out of both of these?
Negative 12.
A 12x squared.
And an x squared. Okay, and what would you be left with?
Y to the fourth minus x to the fourth.
Y to the fourth. Y to the fourth.
Minus x to the fourth. No,
Minus?
Plus x to the fourth.
Plus x to the fourth. Y'all agree? Because I pulled a negative out of both of these, a negative 12, so that makes them both positive. I pulled an x squared out of this one, so I have y to the fourth. Pull an x squared out of this one, I have x to the fourth. That's all over y to the fourth, but that's all over y cubed, right? Right, we've reached a critical point of this problem. This y squared plus x, I'm sorry, y to the fourth plus x to the fourth is the original equation. And what is that equal to?
A to the fourth.
A to the fourth. And that means I can take this expression right here and replace it with a to the fourth.
Ah.
And so I get this, negative 12x squared, a to the fourth over y to the fourth over y cubed. I've got, oh, sorry, 4y cubed. Oh, I forgot my 4 here. I'm sorry. You saw that? You see that right here? I need a 4, that 4 right here. I'm going to do maybe like 2 more steps and we'll be done. I have a fraction on top of a fraction, right? A fraction on top of another fraction. So I'm going to multiply by the reciprocal. So when I do that, I'm going to get a 1 up here and a 4y to the third here. That's gone. And then multiply straight across, negative 12x squared a to the fourth over 4y to the 7. One more step. Reduce. That's negative 3. There it is. There are 3 problems like that on your homework.
Good Lord.
Where you have to sit there and take the derivative, but the hard part is getting your answer to look like the book's answer. I'm going to bring up the solution manual. Let me see if I can find it.
I have to ask, why would we want to replace the y to the fourth plus x to the fourth with a to the fourth? Because I understood earlier the reason we were subbing in for y prime was so that we would have less information needed in order to find the second derivative. But if you sub in a to the fourth, then you have another thing that you need to be given in order to complete that.
Okay, yeah, so I understand what you're asking, I believe. Hold on, let me bring this up first. I want to answer your question. Yeah, so I think you're making a good argument here. It's like, why do this? Because then I have to know what a to the fourth is. Well, the thing that's good about that, okay, is this. Let's say you don't, right? Let's say you don't do that. And then now I give you a point, right? An x and a y. You're going to have to take whatever that x is, raise it to the fourth, whatever the y is, raise it to the fourth, add them together, right? You're going to have to do that. But a to the fourth is a constant, right? You don't have to do anything with it. Like it's fixed. You have to imagine that this problem might be presented to you in this way. okay, with an actual value for A. And then if you had this, then you would say, oh, okay, well, then I'm just going to replace this right here with, 3 to the 4th power. And it's really not anything more you have to do. But it's a good argument. It's a good argument. You could have left it and you still would have got the same answer by just plugging in X and Y. The thing is, this is a very clean version of the second derivative. I mean, that's pretty simple, right? Just replace X and Y here, replace A, and there's not a whole lot of arithmetic to do. So I don't know if that answers your question. Really, this is about playing with the algebra. Can you play with the algebra enough to make it look very simple at the end, which is a good exercise. Because simplifying things algebraically a lot of times is hard, but it can really be beneficial long-term in your math life to be able to simplify things algebraically. Okay, so I just did this one. And there's the answer right there. You can see that. -3 a to the 4th x to the x squared over y to the 7th. They did that in a lot fewer steps, didn't they? They may have left some details out, huh? That's the way solution manuals are a lot of times. All right, so kind of messy, huh? That's problems in your homework. 25, 26, and 27 are like that. So I recommend you make sure you try those and see if you can your answer can look like the books.
And that's on the 2.6 homework?
That's on the 2.6, yes. All right. So now I'm going to try and start to lead us into the next section. And to do that, I want us to just kind of take a step back. And I want us to look at an equation. I'm giving you x squared plus y squared is 100. And I'd like us to take 3 different derivatives of this. The first derivative, I want us to differentiate with respect to x. On the second one, I want to differentiate with respect to y. And on the third derivative, I want us to differentiate with respect to t. And you'll notice there is no t in the problem, right? So let's see how we're going to do this. The first one, if I differentiate with respect to x on both sides of that equation, then move this over here. Let's see. I haven't done my little calling on you through the chart thing. I know I try, but let me see if I can find where the heck is my roster. Where are my rosters? Let me see if this is it. Yeah. No, that's not it. Okay, I don't want to waste some more time. All right, let's just go. Let's just go. So the derivative, I'll just go off my camera. Jasmine, are you there? Jake Flores?
Yeah, I'm right here.
I think, didn't I call y'all two last time? I think I did, right?
You called on me last time.
Yeah, let's go to Josh. How about Josh Mallett?
Yes, sir. So the derivative for A would be 2x plus 2y times y prime.
Okay, so you're saying y prime because we all agree that y prime is dy dx, yes?
Yes.
Okay, I'm going to go back to dy dx.
Okay. Yeah, since we're using all these other derivatives as well.
Yeah, because there's all these other derivatives. Let's just make sure we're clear on it. Okay, I agree with that. How about the right-hand side?
It should just be equals 0 because it's a constant.
Okay. Good. Now, if I wanted you to solve for dy dx, you could, right? We're not going to. Is that all right, everyone? Okay, let's go with Marianella, is that right? No, Marianella. How about Bethany? Derivative with respect to y this time of x squared plus y squared on both sides here. Derivative with respect to y of 100. So how do you feel about the left-hand side?
I think I can do it.
Okay, go for it.
Would it be 2x dx over dy plus 2y?
Yes, good. Equals?
0.
0. Okay, the big difference there now is that because we're differentiating with respect to y, right? That when we do the y part, it's as you would expect, like back in the old days, just 2y. But when you're doing the x squared this time, you've got the chain rule is going to have an impact. 2x, then the derivative of x itself, which is dx dy. Are there any questions on that? Okay. So Daniel Wilson, I'm going to call on you because we talked earlier, and I think you got this now. How do you feel about the derivative with respect to t of this?
Feel good.
Okay, so go ahead.
That'll be 2x times dx over dt.
Good.
Plus 2y times dy over dt equals 0.
Good, perfect. See, on this one, because t is not x and not y, you have to chain rule them both. And neither one of these, dx dt and dy dt, neither one of those are actually going to turn into a 1. Perfect.
So how would we solve that? Like,
it depends on what you would want to solve for. Like, would you like to solve for dx dt? If you could isolate it, right?
Okay.
If you wanted to solve for dy dt, you could isolate it.
Okay.
We're going to do problems where we need this today. So stand by and you'll see exactly how this is going to work.
Gotcha. Coolness.
All right. That equation looks familiar. A equals pi r squared. Isn't that the area of a circle?
Yeah.
Okay. So take a minute on your own here to see if you can answer part A, B, and C. All I want you to do is differentiate it. You don't need to solve for it. Just differentiate and see what happens. Do I need to remind you that pi is a constant? But I just did. Let's take like 3 minutes. That'll give you a minute per problem. Okay, I think that's enough time. See, I can't find the roster. I don't know what happened to it, but I'll try and go off of the, if I've already called on you, just tell me. Because your video, where you are on the video keeps on like switching on me. So that's one thing I've been requesting from Zoom is a way to order the participants, like keep them in alphabetical order or something. It just randomly shuffles you.
Yeah, I think it jumps us around whenever someone unmutes.
Yeah, it's I'm not quite sure how it works, but okay. Let me see. Jasmine, did I call on you already?
Yes, I'm sorry. But I think I can answer the first one.
Okay, go with the first one. So
okay,
we're taking derivative with respect to A on both sides. Go ahead.
Okay, so for the right side, I'm not too sure if I did this right. So for the right side, can we do, I got 2 pi r and then times d over dA.
dr over dA, yes?
And then
yeah. What about the left side?
The left side, so that one I kind of was a little stuck on. Would it just be A or would it go to
it's dA over dA, right? It's dA over dA, which would just be 1.
Okay.
So this would be 1 here.
Okay.
That clear to everyone? The derivative of A with respect to A itself is 1. That's kind of like the derivative of X with respect to X is just 1. Over here, the pi came for the ride, right? But then we have to take derivative of R squared. So 2 comes out, 2R. Jasmine put the pi behind the 2, that's fine. That's the way I would do it too. And then R, and then chain rule, you have to take derivative of R with respect to A, which is dr dA. We don't know what that is. No questions there?
Yes, sir. Quick question.
Yes.
So A is not a constant?
A is not a constant here. Well, in this formula, the only thing that's held constant here is pi, because this is the area formula for a circle, right? So the area depends on the radius. They change together, right? Area is not constant, right? If you change the radius, the area changes. I know what you're asking me because I said, if you see A, B, C, D, they're constants. That's usually lowercase a, b, c, d. If you see something like this, where it's a formula we've seen before, like in our pre-cal or something like that, then that's something where we need to just understand what's held, what is constant, what's not. The only constant here is pi.
Thank you.
Good question. All right, let's see who's up. Vasily, do you want to try the second one?
I don't know if I can do it.
Okay. Well, let's start with the left side. What would the derivative of A with respect to R be?
dA over dr.
Yep, dA dr. That's it, right? We don't know what that is. Whatever it is, that's what it is, right? dA dr equals, okay, over here, we're taking derivative with respect to R of pi r squared. So pi can come for the ride. Now, what would the derivative of R squared be, Vasily, with respect to R?
2R and D.
D, if you're going to do a D, it would have to be dr dr, because now what you're doing is you're taking the derivative of the R itself, but with respect to R. So dr dr would be 1. We don't need this dr dr here, but if you want to continue to think chain rule, then that's what you have to see is there. So we don't need that, right? That's really like a 1. So I'm just going to get rid of it. That'd be your derivative. Yeah, you can put the 2 in front of the pi. All right, let's see who's next. Emily, you want to try the last one?
Okay. So would it be like wait, let me look at the thing. It says D. to like dA over dt, and then it equals like
equals.
I feel like I'm probably wrong, but I guess I'll just say it anyways.
Yeah, say it.
2r pi times like dr over dt. I don't know.
2 pi r times dr over dt. Is that right, everyone?
Probably.
Looks right to me.
That's correct.
Oh.
So the pi comes for the ride, right? The pi comes for the ride. And then you take derivative of r squared, which is 2r. But then you have to take derivative of r with respect to t, which is dr dt. That's not 1, so I have to keep it here. All right? Good. All right. I think we have what we need in place here. The main point of these examples is to show you that if you have an equation and you're differentiating with respect to a variable that actually appears in the equation, then some of the things are going to turn into 1s, right? Some of these things will turn into 1s. If I differentiate with respect to a, then something in here is going to turn into a 1. If I differentiate with respect to r, then something in here is going to turn into a 1. Like when Vasily did that very last step, dr, that turned into a 1. But if you differentiate with respect to a variable that is not in the equation, nothing turns into 1, right? dA dt, dr dt, right? Nothing goes to 1. All right, I think we're ready. Let me open this up. I had this all ready to go until my power went out. Here we go. All right, 2.7, related rates. We've now reached one of the most exciting and useful sections of this course. We now study the applications of differentiation to related rate problems. This will be one of the most challenging sections of the course. Students often struggle with this section because it involves word problems. I admit that these are intimidating at first, but I assure you there is a systematic approach to these problems. And once you figure out how to translate the given information into the mathematics, you might just come to enjoy this. As you will see, there is an expectation here for you to know some geometry, trigonometry, basic formulas for areas and volumes. Don't hesitate to Google a formula if you don't know it, and also be very aware of what's on your formula sheets. So if we have a formula where we need the volume of a sphere, you need to know that your formula sheet has that on there, okay? So you might want to take a look at that formula sheet just to kind of like familiarize yourself with what it has and what it doesn't have, okay? We will begin slowly and work our way into more involved problems. So I'm going to start with a procedure, all right? So I say here, although there is not a cookie cutter way to do every single problem, there are some helpful steps you can follow. So these steps really don't make a whole lot of sense until we actually do an example, but these are helpful steps, all right? First thing we always want to try and do is draw some pictures. We're going to draw pictures. We're going to assign variables. Anything that's constant, we're going to make sure we label that on our picture. We're going to try and write down some equations. We're going to write down the things that we're given, the things that we're trying to find. We're going to have to use implicit differentiation in here, and then we'll get a solution. All right. So all of this, don't worry about these steps. Okay. Don't bother yourself with them. As we do a problem, I'm going to refer to them. Now, I sent you a sheet, a thing in email earlier today, and this is it right here. I am okay with you having this sheet on your next test. You'll have to print out a few of them. That way you have a couple like ready to go. You can use this to do any related rate problem. You can use this worksheet to do it. So there's different things we'll do, right? We'll draw pictures, all this stuff. I'm going to use this sheet today to actually work through some problems, all right? So right now you should be going into this with a very like you should have no idea what we're trying to do at this point, okay? Other than these things called related rate problems. So what I'm gonna do is, first, I wanna bring in that sheet into my document here. So I have it. There it is. Come on. Oh my. There we go. It's a little too big. Let me move it over. That should work. All right, you ready for the first problem? Let's just do it. Come on. I want to make sure, yeah. Okay, here we go. The first problem we're going to be looking at is this example of an expanding circle where a radius is increasing at a constant rate. So imagine that you have a circle, all right? We know that when you have a circle, right, you have a center of a circle, and then you have the radius, and then you draw a circle, right, from the radius. Imagine what I'm doing is I'm basically grabbing the radius and I'm pulling it. And so as I pull it, it creates a bigger and bigger circle, right? As I'm pulling that radius out, making the bigger circle, I'm telling you that I'm pulling the radius at a constant rate. So I'm not like pulling real slow and speeding up. I'm not pulling real fast and slowing down. I'm pulling at a constant rate. And you have to try and visualize what's happening to this circle as it grows. So here it is. Here's an animation of what I'm talking about. All right, so you look at that circle as it grows and try and, let me make it a little bigger for you. Try and wrap your head around the idea that the radius, like if you were to be grabbing the edge of that, does it look to you as if the edge is being pulled out at a constant rate? Almost like if this was a point, that point is being pulled out at a constant speed, right? Does that look like what's happening to you all when I play this animation?
So it looks like.
Looks like it to you? If it helps, look at this up here. I have the computer actually telling me what the radius is. And notice how it grows, right? Right there, the radius is 1. And then now it's 2. And then it's 3. So it's just constantly growing. That makes sense? So I'm pulling the radius of the circle is growing at a constant rate. How about the area? Is the area growing at a constant rate? So no. Watch this area right here. See, the area is real small. Now it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22. Am I speeding up? Feels like I'm speeding up.
Yeah.
22. It seems like I'm speeding up, right?
Yeah.
So even though the radius is growing at a constant rate, right? The radius is growing at a constant rate. The area is not growing at a constant rate, right? Can you all see that? And you can think about it this way. If I were to stop this, let's say right here, okay, the radius is about 2, right? And what's the area? When the radius is 2, the area is what?
13.
About 13, okay? Now, if I go now and I increase that radius from 2 to 3, about three, somewhere around there. Now, when the radius is 3, the area grew to be 28. So when the radius changed, when I added 1 to the radius, how much did the area grow by?
15.
About 15, right? Make sense? Let me change the radius by 1 again. I'm going to move the radius up to 4. Pretty close. So now when the radius is 4, it's grown by 1 again. Did my area go up by 15 again?
No.
It went to about 49, right?
It went up by like 22.
21 or 22. It grew faster in that next increment, right? Let's do one more. If I go from a radius of 4 to 5, somewhere around there, my radius is 5. The radius grew by 1, but the area now jumped up to about 80. So yeah, that's a jump of what?
Almost over 30.
Yeah, it's like 31. So even though the radius keeps increasing at the same rate, the area is increasing even faster, right? You know with me? So what we're interested in is this, okay? This is the calculus question. If you were to take this circle, right? And let me let it start over. If I were to say to you, all right, ready? Everyone see that moving? At exactly the moment I clap my hands, right? I'm just going to make up a point in time here, right? Right then, when I clapped my hands, right at that instant in time, how fast was the area changing? At that instant in time. I know you can tell me how much the area changes on these increments of time, like between 2 and 3, yeah, you can tell me it grew by 15. Between 3 and 4, it grew by 21. That's like an average rate of change. What we want to know is the instantaneous rate of change. Does everyone I need to make sure everyone understands the actual physical problem before we can try and answer the question. Radius is growing, constant rate. We want to look at a specific instant in time. I want to know how fast the area is changing at that exact moment. Yes?
So question.
Yeah.
So I'm just thinking that's a parabola, right?
What?
That formula, if you were to graph it normally, it would be a parabola, wouldn't it?
What would be a parabola?
A equals pi r squared.
Oh, a equals pi r squared would be a parabola, yes.
Yeah. Mm-hmm. Okay. I just wanted to double check that because looking at it, that looks like a parabola.
And that's the relationship, right? We do have an equation that relates the area and radius together. Area equals pi r squared. So there is some sort of quadratic relationship between the two. This whole idea of trying to figure out how fast something is changing at an instant is so important because that's what calculus is all about. Here's another analogy. Let's say I'm running, right? Y'all are watching me run. And then I say, ready, everyone, freeze. And right at that instant, I ask you, how fast am I going at that instant in time? Well, there's a couple of problems with that. If I freeze, right? If all you're looking at is me frozen, I'm not moving, right? So you can't say I have a speed. So you're not allowed to freeze me, but you are allowed to ask, if I'm running, you are allowed to say, right then, okay? Don't freeze me, but right then, at whatever moment you're interested in, ask about the speed. We get to this whole 0 over 0 thing, but we know we have a way around it, right? That's what the derivative is all about. So let's actually get this problem. I was just trying to construct the visualization of it, okay? So here we go. Here's the problem. This is the way it would be presented on a test, all right? Or on a homework problem or something. Here it is. Make it a little smaller. Okay. If the radius of a circle is increasing at a constant rate of 0.5 feet every second, then how fast is its area increasing when the radius is 4 feet? So again, we have a circle. We're being told that the radius is growing at a constant rate. And we want to know at a specific moment in time, exactly when the radius hits 4 feet, at that instant, how fast is the area growing? All right, can I proceed? I need to get to this sheet here. Everyone got that? All right, so on my worksheet, what I have is positions for you to start drawing things. I have an instant and a general basically we're going to try and draw two pictures. One picture is going to be the instant in time that we're talking about. The other picture is the general picture. Which one you draw first doesn't matter. I'm going to choose right now to draw the picture in its general form first. I have a circle, right? I have a radius. That radius is R. I'm not going to fix it. I'm going to imagine that that radius is moving, right? So my general picture is just the physical construct of what's happening. I have a circle with some radius. The radius is moving, right? It's growing, but that's my general picture. Now, at the exact instant and moment in time we're talking about, I have that circle, but now I can tell you what the radius is. What's the radius at the moment we're talking about here?
4.
4 feet, right? Because we're asked how fast is the area increasing when the radius is 4 feet. So here I can fix it at 4 feet. So you're supposed to imagine that this circle is moving, right? So you can't fix R. You can't tell me R is 2 or R is 4. It's moving. Here though, at that snapshot, like the runner running, right? That's the moment that we're talking about. This is the picture on the left. All right, I've labeled this. This has a radius, right? I've assigned a variable to it. Here, I've assigned that variable a value at the exact instant in time. Let's talk about what we're given and what we want, okay? So what am I given? In here, I'm told that if the radius of a circle is increasing at a constant rate of 0.5 feet per second. Okay, when you see the word rate of change, derivative, right? That's what a derivative is. It's an instantaneous rate of change. We are given here this 0.5 feet per second is a rate of change. It's the rate of change of what?
The radius.
The radius, right? So this is telling me that my radius is changing at this rate. Yes? So this 0.05 is a rate of change of my radius. It's the rate of change of my radius with respect to time, right? Look, feet per second, feet over seconds. The bottom is seconds, the bottom is time, right? So what I'm gonna do here is on this right here where I'm given, I'm gonna write down dr dt is 0.5 feet per second. Now see, after I've written that down, see if that makes sense to you. The instantaneous rate of change of R with respect to time is 0.05 feet per second. Do y'all see how that translates from the word problem right there? If the radius has a rate of change of this, then that means the derivative of that with respect to time must be this. Questions? What do we want to know? What is it we're trying to find?
Yeah.
How fast, right? Fast is speed, right? I'm talking about the speed of something. If I'm talking about the speed of something, I'm talking about the derivative of it, right? Speed is derivative. Derivative is speed. So I want to know how fast what's changing.
The area.
The area is, right? How fast the area is changing. That means I want the derivative of the area.
Yeah,
So
with respect to the radius, right?
I want the derivative of the area with respect to time, right? That's what I want. This is what I want to know. How fast is that area changing with respect to time? But I don't want it at just some arbitrary point in time. Don't I want it here at that exact moment? So I need to put here in what I want. I want to put, I want dA dt. I want that at the moment that R is equal to 4. I'm going to zoom out just a little bit here. Okay. I'm given the speed of the radius. Boom, dr dt is this. I want the speed of the area, dA dt, but I want it at exactly the moment that the radius is 4. With me? Questions, comments? Okay, so what about the steps? I want to kind of read through these steps a little bit. Draw a picture of this scenario at the exact moment we're talking about. I've got that, check. Okay, draw a picture of the general situation. Okay, yeah, I've got that. Assign variables, check. Assign variables and constants. Yeah, I think everything's in place. Okay, I only have one thing, radius, right? Now, this is the key. Once we've got everything written down, we've got what we want, what we're given, all that. This is the key step. Find an equation. Any equation that exists out there, any equation that relates what you're given to what you want. So what I mean by that is I'm going to look over here at what I'm given and what I want. I'm going to look at the main variables in this problem, R and A, radius and area of a circle, right? That's what we're talking about here, a circle. I need to find any equation that exists out there that somehow connects the area of a circle to its radius, which we all know, right? We have that equation. So what I'm going to do is write that equation down. A equals pi r squared. That has both A and R in it, right? Check, got the equation. The next step is to use implicit differentiation to take the derivative of that with respect to what?
Time.
Time, because look, we know what happens to R with respect to time. We want what happens to A with respect to time. So if we have an equation, why not differentiate it with respect to time, with respect to T? We know what will pop out, right? I mean, let me do my implicit differentiation. I'm gonna do it down here. I'm taking the derivative with respect to T of the left side, and then the derivative with respect to T of the right side. You should know now that when you do this, you're going to have both a dA dt pop out and a dr dt, right? Both of them should pop out of this equation. So we did this on the previous example right before we started the session. This became dA dt, and the other side became 2 pi r dr dt. There's your implicit differentiation. This is the master formula now. This relates everything together. So I'm going to put that right here. And now what we can do is the last step, plug in all constants and everything we want for the exact moment in time. So do we know what dA dt is?
No.
No, right? But that's what we want, right? That's what we're trying to solve for. 2 pi is a constant. Do you know what R is at the exact moment in time?
Yeah, it's 4.
Yeah, it's 4. Okay, good. Do we know what dr dt is?
Yeah, 0.5.
Yeah, 0.5 is given to us. We have everything. In this formula, we have everything we need. So this will become dA dt equals 2 pi times 4 times 0.5. And notice I'm not putting any of the units on here. Like I didn't put 4 feet and I didn't put 0.5 feet per second. I didn't put any units. You'll see why in a moment. Let's go ahead and multiply out the right-hand side. dA dt is equal to, let's see, I'll do that first. That's half of 4, that's 2. And then 2 times 2 pi, that's 4 pi. Now I could get a decimal answer for that on my calculator, but I'm not going to. I'm just going to leave it as 4 pi. So my answer is 4 pi. That's how fast the area is changing at that exact instant in time. But I need the units on this. I need what units to use. So what you should do is look at your two variables here. A stands for area. How do we measure area of things?
Square meters.
Squared units, right?
Yep.
Squared units. So what were our units in this? What was the measurement?
Yeah, this is all going off.
Feet, right? Wasn't it in feet? So the top, this top should be feet squared per the time on the bottom. How are we measuring time in this problem?
Seconds.
Seconds, right? Seconds. There it is. Well, that should be our solution.
So area is always going to be represented by a squared value.
Say again?
Area, like whenever we're, showing it in some form of area, it's going to be always a squared value.
Yes. For the units, if we're talking about area, it'll be whatever the units are squared. If this is a volume, it'll be the units cubed. If it's a length of something, it'll just be the unit itself. All right. So I hope that you kind of can see just how powerful this whole idea of implicit differentiation is. It basically gives us a way. Well, think about what we've done. I gave you the rate that one thing was changing, right? I told you that the radius was changing at a certain rate. And then you were able to tell me the rate at which something else changed, right? I told you how fast the radius was changing, and you were able to tell me at an instant in time how fast the area was changing. Somehow we found a way using calculus to take those two rates and relate them together, right? Related rates. That's the name of this section, related rates. We are trying to relate rates of change to each other within physical geometrical problems. Okay. Different scenario. Still a circle. Here we go. Different problem. It's hard to notice what's happening here.
The rate that the radius is increasing is slowing down progressively, isn't it?
The rate that the radius is being pulled out is slowing down, right? Do you see in the beginning it was really fast and then it gets slower?
Yep.
Right.
Is it trying to keep the rate that even the rate the area is changing is managing to slow down?
Nope. The rate that the area is changing is being held constant here.
So it's happening. Okay. It's hard to tell.
It's hard to tell. It's hard to tell. But the change here, this problem is different than the other one, that we're not pulling the radius out at a constant rate. We're making the area change at a constant rate. And so you have to slow down, because once you have a big circle, if you change the radius just a little bit, you get a huge area added. If you have a small circle and you change the radius a little bit, it adds area, but not as drastically as if you have a huge circle and you add a little bit of radius to it. So maybe you can tell, just look at the area counting. I'll slow it down just a little bit. So just look at the way the area counts here. It's going to start over here. Watch. It's coming. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So see how the area is just constantly going up? 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. This area is not speeding up or slowing down. The radius, on the other hand, is, watch in the beginning, it's going to get real big fast. Whoa, it's already up at 1. Now it's 2. Three, that took a while. 4, right? So it's taking longer and longer for the radius to go up by 1, but the area is just the same thing. It just keeps ticking up by 1. So I'm going to give you this problem. I'm going to see if you can do it. There you go. See what you can do with that in the next 7 minutes. So I know it hasn't been 7 minutes, but we're almost going to run out of time. So I wanted to just try and run through this quickly. The pictures of this are very similar. We still have a circle. It has some radius, and that radius is changing, right? We have at the instant in time. What can you tell me about the instant in time?
That our area is at 5 feet squared.
5 square feet, right?
That's our instantaneous rate of change.
Yep. Well, that's our value of the area at the moment in time.
Oh, yes. Yeah.
That's all I can say. We've got a circle, it's changing, and then over here at the instant we're talking about, we are talking about how fast the radius is increasing when the area is 5 square feet. So let's talk about what we're given. If the area of a circle is increasing at a constant rate of 1/5 square feet per second, that is a derivative. That's the derivative of what?
dA over dt, isn't it?
The area, right? It's the rate of change in area with respect to time is 1/5 square feet per second. That's what we're given. We would like to know how fast the derivative of the radius is, right? That's what we want. How fast is the radius changing? So here we want dr dt. But we want it at exactly the moment that the area is 5 feet. Once we have this, we just need an equation relating the two together, A and R, which we use the same formula, right? A is pi r squared. We can differentiate that equation with respect to t again. dA dt. So it's the same mechanical formula, isn't it? 2 pi r dr dt.
We're going to try and find dr dt this time?
Yeah. Oops. Whoa. The big difference is that we want to know what dr dt is, right? So if I write this equation down, dA dt equals 2 pi times r dr dt. When I start looking at this, now pay attention, this is a critical point here. When I start looking at this, dA dt, I'm happy to see, right? Because I have it. I know what dA dt is. dr dt, I'm happy to see because that's what I'm trying to solve for, right? But I also need to know what r is. And r is not given over here, is it?
We can't find it though.
We can find it though, because now we can use the circle at the instant in time. And if the area is 5, that means that 5 is equal to pi r squared. And we can solve this for r by dividing by pi and then taking the square root. So I know that at this instant in time, at the moment in time we're talking about, I know what the radius is. So I can start filling all these pieces in. This is 1/5 equals 2 pi. The radius is the square root of 5 over pi. And then dr dt is what I'm trying to solve for. And then at this point, we can just use a calculator and figure out what this is. And that will be our solution.
It's awful.
Yeah. It's what?
Awful.
Well, it's, yeah, just use your calculator. Just get a decimal answer.
So, sir, what I tried to do was separate R and before I just took the derivative, and I think that would give me the same thing. But in general, do you think taking the derivative before you try to isolate R, if you have to like algebraically alter equation, is better, or do you think it's just a matter of depends on the equation in question?
Okay, so if I understand Josh's question, what you did is you wrote down the equation of a circle, and then you said, I'm going to need to know what dr dt is, right? So you tried to solve this equation for r first?
Yeah, basically I changed it to a divided by pi equals r squared, and then the square root of a divided by pi equals r.
That's fine. That's fine. However, this differentiation is going to be a little harder. The right-hand side, when you take the derivative with respect to t, you'll get dr dt, right?
Yeah.
That's this. But when you take derivative of this with respect to t, you've got chain rule.
So, yeah, that's what I noticed. Yeah.
So I think it'll be an uglier thing. The thing is, once we have an equation, we can just, that's the whole beauty of implicit differentiation, is that you don't need to solve for the variable that you're interested in. You just differentiate. So my recommendation would be just go here to here.
I will keep that in mind in the future, because I think your method was a lot neater than what I was trying to parse out. Like, I think I could, I just think it would slow me down.
Yeah, it would work. It would work, definitely. As long as you did the derivative right, it would work. Okay, so look, we're just getting our toes into the water here, all right? So for the homework for this section, 2.7, I only want you to look at those three problems. Numbers 5, 6, and 11 for 2.7. 3-word problems. One of them has to do with a cylindrical tank that's being filled up with water. Another one has to do with a sphere, not a circle, a sphere. And the other one has to do with a melting snowball, which is basically a sphere. All right, everyone got that? 5, 6, 11. Now, I know it's time to go, but I wanted to kind of show you kind of where we're headed with this, some of the problems that we'll be doing. This is a good one. A plane is flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. So you got this plane that's 2 miles high, traveling at 600 miles per hour over the ground. The plane is headed directly over a ground-based radar station. Okay, so there's some radar station on the ground. Here's the plane coming over, here's the ground. And it says, at exactly the moment the plane is 6 miles from the radar station, how fast is the angle of inclination or the angle of the tracking radar station changing? So if this radar station is like tracking the plane through the sky, at exactly an instant in time, how fast is this having to turn to keep up with the plane that's traveling through the air? So this is a picture of what I'm talking about. Let me back this up. So you have a plane, which is the blue dot. You have a radar station on the ground. As the plane travels across the sky, notice the angle here changes, right? The angle changes. But if the plane's traveling at a constant rate, watch the angle and how fast it changes. So here comes the plane. Watch the angle. Slow, fast, slow. Right? Slow, fast, slow. It's almost like if you're standing on a train track watching a train go by. You look down the track, you see it, your head slowly turns, and then as it gets closer, it's like, right? And then so your angle has to like speed up and then slow down. That's what's happening here. So we want to know at a specific instant in time, whatever that instant is, how fast is that thing rotating? We have to somehow relate those rates together. Streetlight problem. You can go if you need to. A street light is mounted on a 20-foot pole. A 6-foot man walks away from the pole at a speed of 7 feet per second. How fast is his shadow moving along the ground? So you got this person, the person's in red. You have a pole 20 feet tall with a light on it, right? So as this person moves, right, think about what the light's doing. The light's shining out from here, right? The light comes, and when the light hits him, right, it creates his little shadow on the ground. That's the man's shadow on the ground, right? And so as he moves across the ground, as he moves, his shadow is changing. So the question is, at a specific instant in time, how fast is his shadow moving? Let me show you the shadow. See his shadow right here? The black? We want to know how fast it's moving. Is it the same speed as the man? I don't know. We'll see. Last one. A conical cup is being filled with water at a constant rate. How fast is the water level coming up the cup? So we have this cup. It's a conical cup, and we're going to start filling it with water. We're pouring the water in at a constant rate. How fast is the water level coming up? Well, it depends. Are we talking about when it's really low, right? Because in the beginning, it comes up really fast because it's very narrow at the bottom. But as you get to higher points in the cup, the water level comes up slower. So we want to know, like at a specific instant, whatever that is, how fast is that water coming up the side of the cup?
So our answer is going to be a formula.
Well, our answer is going to be a number.
Oh, what, did it ask for a specific point?
Yeah, it did. It said,
how
fast is the
water
level rising when the water is 1 inch from the top of the cup? So that's our specific instant in time.
I didn't catch that. I thought it was just asking what the general rate was. I was like, oh, okay.
A person is running around a track at a circular track, okay, at a constant speed. Right? You've got another person who's watching them, their coach or whatever is watching them. At a specific instant in time, how fast is the distance between them changing? So if we look at a line that connects the two together, this line is changing, right? So we want to know at a specific point in time, wherever that might be, how fast is that green line changing, growing or shrinking? This starts to get you to see how this could be used. Like, just think about an engine, and you've got like pistons attached to a crank, right? And you've got spinning happening here, and circular motion here translates into linear motion. And so if you want to know if the crank's turning at a certain speed, how fast the piston's moving, this is all this is kind of building up to that sort of being able to do that sort of problem. So anyway, yeah, there's so many different ones that we can do. A balloon gets let go. Ooh, that was really fast. Why was that so fast? That was really fast. Yeah. There's another one where you have like a ship that starts sailing north at a certain speed, and then like an hour later, a different ship starts sailing east at a different speed. So 10 hours later, like how fast are they moving away from each other? I mean, there's all sorts of problems, but they're all word problems. And so, yeah, we're in for some fun on what, Thursday? So do those 3 problems, be back here on Thursday. We'll do nothing but word problems on Thursday.
Oh boy.
Okay, have a great one.
You too.
Have a good day, Professor.
Bye, thank you. Have a good day.
You too.
Did you